Okay, next I want to talk about divisibility, which is an extremely important concept in number theory. Let me start with the definition. So here's a definition. Given A and B in the integers, we say A divides B. This is the statement. This is, and we write it like this: A and then a vertical bar B. If and only if, so this definition is if and only if basically A goes into B evenly. So if only if there exists an integer K such that A times K equals B. That's the definition of divides. And so we read this just the same as we say A divides B. So we read it that way. Okay, just as some quick examples, just to make sure we know what we're talking about here. 2 divides 6 is a true statement. So I'm gonna be a little careful and make this like a vertical bar. 2 divides 6 because 2 times 3 equals 6. 100 divides 1,000 because I still didn't make this very vertical. Because 100 times 10 equals 1,000. 3 does not divide 7 because we can't find, because 3k equals 7 does not have a solution in integers. You could ask for sort of axiomatic reasons why, which we might talk about in some other videos. So certainly if you allow rational numbers, it becomes true. You could 3 times 7/3, but we're not saying that here. We're just saying we want an integer, right? One thing that is worth pointing out at this right now is that it's important to notice what a statement like if I write something like 2 divides 6, this is actually a sentence. It's important to like think about the grammar of mathematics sometimes. So in fact, I really should have a period. Like if I just wanted to say like, 13 divides 39, I would actually put a period when I write math, because it's like noun, verb, noun, verb, noun, right? 13 divides 39, subject, verb, object. And it's a true sentence. That's a true sentence. Versus something like 13 divides 38. That's a sentence, but it's a false sentence. Versus something like 39 over 13. This is a noun, right? 39 over 13 is just an expression. It's not a sentence. This is a noun. You could say it's a noun that equals 3 and you'd be right. Well, it's a number that equals 3. As a noun, you could set it equal to 3, and so you could say 39 over 13 equals 3. That would be a sentence. But this is a noun. And so just some people kind of mess up the which direction. You put the smaller number first, really, because that's the number that goes into the larger number. Okay. So just try not to like mess yourself up with this. Okay. And that's why I was trying to make these more vertical. Okay. Let me ask you guys a question for you to think about and try to answer in your notes. Which of the following are true? 0 divides 3. Is that a true sentence? 3 divides 0. Is that a true sentence? I'm trying to make these pretty big vertical bars. 0 divides 0. Is that a true sentence? Think about that. Try to answer it in your notes. We'll discuss it in class. All right. I want to mention also other rings. You can actually you can develop divisibility is a definition that works in any ring. So, for example, we're going to look at this. I mentioned this Z adjoint I. So I claim, for example, that 2 plus I divides, I should use the notability straight line function, like just hold it and then it becomes a straight line. Divides 1 plus 3I. I claim that's true because, well, if you multiply 2, you can try this yourself. You multiply out 2 plus I times 1 plus I. If you FOIL that out, try it yourself, you'll actually get 1 plus 3I. And so, and 1 plus I is an element. So this is true. This is true in, it's a statement that's true in ZI. It's always important to remember what ring we're actually in, because even up here, I could say this is this example here is false, but only in Z. If I could say it's true in Q, in the rational numbers, right? Because 13 times 38 over 13 is 38. So that's true in the rational numbers, but it's false in the integers. So you always want to note what number system you're in. Okay. There are some properties that aren't that hard to prove from axioms, from even just the ring axioms. So let's just say given A, B, and C integers, one property is that if A divides B and A divides C, then in fact, you could say A divides B plus C, A divides B minus C. Maybe the most strong thing you can say is A divides an expression in the form BX plus CY for all X and Y in the integers, right? You can make any multiples of B and C and add them together. Like if B and C, think about a specific example. If B and C are both multiples of 3, so if A equals 3 here, and you add 2 multiples of 3, you get another multiple of 3. If you multiply a multiple of 3, you get a multiple of 3, right? If I take 9 and multiply it by 10, I get 90, which is still a multiple of 3. And you can actually combine them to be in any sort of, this is actually called, there's a word for this, which I'll mention. This is a linear combination. Of B and C. So if B and C are multiples of A, then BX plus CY is also a multiple of A for any X and Y. Another one is sort of like there's a transitivity statement. If A divides B and B divides C, then A divides C. It's not too hard to prove by writing out the definitions. One last question before I end the video. One thing we'll think about quite a lot in number theory, it comes up a lot, is this. If A divides the product B times C, can we say anything? Does that mean then A has to be a divisor of B, or A has to be the divisor of C? Yeah, like if you're basically thinking that A is a divisor of B times C, A divides BC, does that mean A lives inside B, A lives inside C? Neither, both. If it's not always true, are there for certain A, does this work? Something we'll explore and we're thinking about. Or if you know A doesn't divide B, so like if A divides BC and A doesn't divide B, does that mean, does that force A to divide C? Anyways, these are, it's sort of worth thinking about. This comes up. You might have a sense. This is the word certain, which is hard to read. That's a question mark. Okay, so just something to think about. You can, that was a little harder to, I think the other question I asked you can answer directly in notes. This you might try to come up with some examples. But all right, I will stop there.